Okay, so welcome to lecture 2 on functional and structural testing. In the last lecture, in the introduction to digital testing of VLSI, so what we have seen is that in case of circuits, testing occupies an important paradigm, because in case of circuits, the technology being adopted is so new and it is currently changing in such a rapid way that most of the chips, or you can say a high percentage of the chips, may have failures or defects. That is, the yield is sometimes as low as 50 to 60%. So that is why we have to find out that which of the chips are functionally correct and which of the chips have fault, and then we have to bin them appropriately, and then we have to separate that before we send them to the market. So that is why testing in circuits is such an important domain that we have already seen in the last lecture. Then we have seen that testing of circuits or any system, maybe in the last lecture we have taken the example of a NAND gate. So we have seen that testing can be as simple as just checking the functional properties, like for a 2 input NAND gate, it was for all inputs like 0 0 0 1 1 0 and 1 1, and we just check whether it is functionally proper. Then it can be as exhaustive or as complex as finding out whether the layout from which the chip has or the AND gate has been designed is proper, like the metal deposition should be proper, the thickness between two nets which is being laid out for the NAND gate has to be proper distance of say some x micron, which is as per the design rule checks and so forth. Then there can be delay faults, then there can be so called the transistor level defects and tests. So we have seen that starting from the simple functional testing of the truth table, it can be as complex as checking the layout. But now the problem is that as we have to test millions of circuits for a sample run, and the number of gates in a circuit can be as large as millions. So to test a circuit in full depth, that is maybe to the layout level or at the transistor level, it may take decades or years. So that is why we cannot go to that level of exhaustive testing. So at best, what is feasible, because our idea is that, as we discussed in the last class, our motivation was that we have to apply as minimum test patterns as possible, that is as low test time as possible, but at the same time we have to have a very good what you call confidence or you can say that the accuracy of the test. So that is why today we will see what is actually called structural testing and why we have to move away from functional testing to structural testing. That is the main motivation of today's lecture, that functional testing, that is in terms of the truth table, that is what was the simplest testing in the last class. After that there was transistor level testing, then was delay testing and so forth, and even we will see today that functional testing, that is simple the truth table testing, is also takes a very long time and is not feasible to apply in a real circuit where the number of samples are in millions. So that we have to move to structural testing. So that is what will be our focus today. So let us start with an example. So you can see that this is a 25 input NAND gate circuit. So it actually it's a dot product of all 25 inputs I1 to I25, and inside this you can have a series of what do you call AND gate logic circuit. In this is not shown because it is a quite large circuit. So now you can understand that if I have to do functional testing for this one also, we have to apply patterns which starts from all zeros, that is I1 to I25 all zeros, okay, and we have to go for all ones. So we require 2 to the power 25 test patterns to test the circuit. We start from all zeros and we end with all ones. And what is the expected output? For accepting the last thing, because it is AND for all the inputs, that is I1 dot I2 dot I25. So for all cases the answer should be 0, except in the last case the answer is 1. So for exhaustive testing you require to apply a order of 2 to the power 25 input patterns, which is very large. If you think that if I can even apply a test pattern in the nanosecond range, but if the number of this circuit is in millions, you will take days to do the testing. So which is not actually feasible. So we will progress and we will understand more into this one. So you can see we require to apply 2 to the power 25 test patterns to test the fault, and remember that we are not doing a delay testing in this case. If you had done a delay testing in this case, then you have to apply this pattern followed by this pattern, then you have to apply this pattern followed by this pattern. So you can understand that we have to apply more than double the 2 to the power 25 kind of a faults, because in 2 to the power 25 we just do a functional test. Now if you have to do a delay test, that is delay test is one is the rise delay and one is the fall delay, which you have seen in the last class. So for rise delay we have to apply this pattern followed by this pattern, then this pattern followed by this pattern, and so on till this pattern and this pattern. Then if you want to go for this the fall test, that is from 1 to 0. If this pattern has to be tested at speed, then you have to first apply this pattern followed by this pattern, then again this pattern followed by this pattern, and so on. So, you can easily find out how complex the testing will become even for a simple circuit which is having which does a AND of 25 inputs. So, that is why this is not at all possible. So, even if it's a normal functional test with 25 inputs, no consideration for delay and all, you require 25 test patterns. For delay it becomes more complex. And if you assume that we have a megahertz tester, that is it applies so many test patterns in a second, we require 33 seconds per chip to test the circuit. And remember, it is only simple functional test, and in generally we have about 1 million chips per run. That is, once we go for fabrication, we do not develop or fabricate 1 or 2 chips. In a single run we have around millions of circuits. So, millions of chips has to be tested in a run. So, you can find out, if you do the calculation, you will require this many seconds or this many hours, this many days, or some huge number of years to do the functional testing for a simple circuit having 25 inputs. So, for functional testing cannot be performed due to extremely large number of testing. That is what is the idea. Now, you can think about, this is only a circuit having 25 inputs, and the circuit is as simple as 25 doing an ANDing of 25 inputs. Now, you can think of a circuit like a Pentium chip which is in our processor, or you can think of a graphical processor circuit which can have 512 inputs or 1024 inputs. Then the number of inputs required will be 1024, and then you can understand, instead of this 62 years it can be 62 decades, or it can even be something which our testing will start in our lifetime and will be not alive to see what is the output. What the results of the test, that it may not be feasible in our lifetime. So, you can understand that it is practically infeasible to apply functional testing. Now, you see, so what is the solution? The solution is that we have to bring down this number, that is order of 2 to the power n, where n is the number of inputs. This order is required to do our functional testing. This we can bring down, the number of test patterns we can bring down, or we can move up the test speed. This we can move up, but moving test speed, fine, you can go up to megahertz, you can go up to gigahertz, but going to terahertz or even higher than that will require a tester which will be so expensive that you can never make up a profit by selling the chips. We can make profit by selling the chips if the yield is low, that is, if the 50% of the circuits are defective. So, you can throw out 50% of the chips and other correct 50% you can sell in the market, and you can make a profit. That is absolutely fine. But you can understand, you have to get the idea that if you have to test a chip in the terahertz level or even higher, the test equipment will be so high that you can never make a profit out of using the tester and testing the chip and making a profit out of it. So, AT equipment which we have shown in the last class is a very expensive equipment, and that is the main reason that why we cannot concentrate on, or what we cannot do, that we can take the test speed to gigahertz or terahertz or anything in our level. So, research is still going on to find out if we can have cheaper testers which can apply test patterns in a fast range, but this phase is a very difficult phase to go on. But so, what people have researched on and what people have found out, that if we can do somehow bring out this 2 to the power n, if this number can be brought down, that the number of test patterns which has to be applied can be brought down, but still if you can have a good accuracy, then it can be a very good paradigm of testing, or you can say that it is a very good achievement which you have made. And this is absolutely what people have discovered by statistics. But statistics means statistical results or history has a very important role in testing. So, in testing what you do, you apply a certain kind of test strategy, and then you see what is the outcome for around say 2 to 3 years in different manufacturing industry. For example, let us assume that somebody has found out a technique in which you can apply only k pattern to test a circuit, where this is very less than 2 to the power n. Then we go on using this number of test patterns, and then we keep on testing the circuit, and then we keep on finding out that, keep on doing the binning, that this is a normal circuit, this is a defective circuit, but we do not apply to the power n, we apply only k number of test patterns. Now, you have to find out the accuracy, that what wrong you have done, that is, if there is any case where you have shipped a faulty circuit telling that it is a normal. So, if that is called inaccuracy in testing. But history, if you look at history, people have found out that there can be very good strategies of determining this k number of transitions where the accuracy is very high, even it is as high as 99.9% plus. So, that was a very surprising or what you call very nice invention or discovery you can say, in which people have found out that you can find out there exist strategies in which you can find out the k number of test patterns where k is much less than 2 to the power n, and still your confidence or your accuracy in testing is as high as 99.9% plus. So, therefore, people research actually started taking more in this direction on reducing the test pattern rather than making the test pattern application faster by expensive equipments. So, this bringing down these test patterns to k in number from 2 to the power n can be possible through structural testing. So, we will see what is the structural testing. He is the gentleman who introduced structural testing, and he says that he verifies the correctness and specification of the structure of a circuit in terms of gates and interconnects. Like in a very simple way, you say that I have this is my circuit say. Okay, so, what this circuit does is actually makes an AND of input 1, input 2 and input 3. This is actually a functional test. But for structural test, what we will do is that we will never verify that whether this circuit is doing this ANDing of input 1, input 2 or input 3 correctly. Rather, what it will do is that it will find out whether this gate is operating properly, this gate is operating properly, and whether these interconnects, that is the wires, are correct or not. It has nothing to do that whether it is an AND gate or whether it is an OR gate or whether it is a multiplier. It has nothing to, absolutely nothing to do with this. It only verifies that individual gates and individual internets are proper or not. If that is fine, then they say that the gate is structurally tested to be fine. And people have found that if you can do a proper structural testing, then it is equivalent or as accurate as a functional testing to a very high degree, say about 99.9% plus. So, the main area that or in structural testing or the testing area or the research mainly started moving to developing good strategies for structural testing. In structural testing, it takes many fold less time compared to functional testing, yet maintain the quality of test solution, that is around 99.9% plus quality it is maintaining. Okay, so, as I told you, the structural testing does not check the functionality of the entire circuit. It has nothing to do whether the circuit is an adder or a subtractor or a multiplier or as complex as a processor. It only checks whether the structural units, generally in the units are gates in the general level, the general definition, are fault free as well as the interconnects or the nets are fault free. So, you can tell that structural testing is a functional testing at the gate level. You just verify whether the gates are functionally correct as well as the nets are functionally correct. So, that is a generally we say that structural testing we are doing functional testing, but only at the gate level and not higher than that. So, let us try to explain a structural testing by the example which we were considering in the first slide. So, this is again the same circuit which actually does a ANDing of 25 inputs. Now, functional testing we saw that we require 2 to the power 25 inputs where we started from all zeros to all ones. Now, we will see what we do in the structural level. In structural level, all the gates, these gates are individual elements, and we have to find out whether these gates are functionally proper or not. And we have to find out that whether these nets are correct. So, I mean we see that if you test the gates, automatically nets are checked. So, if you want to find out whether this gate is properly functioning or not, then what are the patterns you have to apply? 5 inputs. So, 2 to the power 5 patterns you have to apply. So, what will be there? They will be 0 0 0 to 5 ones. So, these are the patterns required to test each AND gate. Okay, so, this implementation of the 25 level ANDing is done by 5 AND gates, and there is another AND gate which is actually doing the next level of this thing. This is circuit implementation. There can be any other implementation of this function. So, for this gate you have to apply 2 to the power 5, for this gate you have to apply 2 to the power 5 patterns, and this gate you have to apply 2 to the power 5 patterns, and again for this gate individually you have to apply 2 to the power 5 patterns. So, each gate now I am testing individually, but I am not testing the entire interconnect or what you call the entire circuit entirely. I am not testing. I am testing each gate individually. So, number of test patterns required to test each gate individually is this one, that is 2 to the power 5. So, just a minute. So, now you can see. So, now how many patterns you require for this? It is very less. It is 2 to the power 5 into number of gates is 1, 2, 3, 4, 5 and 6. So, this is 6 into 2 to the power 5, which is much less than 2 to the power 25. So, see what we have done. if you go for the functional testing of the whole circuit, then you have to apply 2 to the power 25 inputs, 25 inputs are available. That is a very high number. But now if I want to say that I want to test this separately, I want to test this separately and so forth, then for each gate you require 2 to the power 5 inputs and number of gates required is 6. So 6 into 2 to the power 5, 25 is a much lower quantity than 2 to the power 20. But now what I have not done? I have not done the integrity testing. But people have shown statistically that if you take this structural testing, still the accuracy of a functional testing is as high as 99.9%. Now you have to understand one very important thing. So what we are doing here? So if you are going for a structural testing, you are applying 2 to the power 25 vectors. But now if you are applying functional testing, then you are applying 6 into 2 to the power 5 test vectors. So the number of vectors being applied is a very less number of vectors. So you can call this 2 to the power n, and this is actually called k, which is as per our last discussion. So this k is much less than 2 to the power n. So structural testing is telling you that you have to apply some 2 to the power k inputs. Now which 2 to the power k inputs is also being told by the structural test, which we will elaborate later. But there is one very important thing you have to note, that we said that structural testing is a very nice thing. Okay, so you can test each gate individually, okay, and you have to apply only 6 into 2 to the power 6 to 2 to the power 5 test vectors, which is much less than 6 in 2 to the power 25 test vectors, and the accuracy is 99.9% plus, which has been seen through history and statistics. But then what you have to pay? See, the thing is not very simple. This gate, if you want to test, so you apply 0, 0, 0, 0, 0, 0, 1 and so forth, this truth table you apply, but you have to observe this output, that this output is connected to this gate, right, and this is a circuit, this is the circuit. Okay. So this line is directly feeding to this AND gate. So this thing is not available to the output to be observed. So one thing you can do is that you bring this as a separate pin out from the circuit. Then it is very easy, you can apply these 5 inputs and you can observe this at the output. Similarly, for this gate also, this gate is directly connected to this AND gate inside, and this is not brought out in the chip. So you can test the circuit, fine, you can easily apply the test patterns, but you cannot observe it directly. So you can bring the pin outs. So that is one thing. So for all such nets, you have to bring pin outs. So now you have decreased the test pattern from 2 to the power 25 to k, but k, which is actually 6 into 2 to the power 5, but now you have to bring lot of pin outs from the circuit. That is actually a very difficult situation, because if you have 1000 nets which you have to observe, then you have to have around 1000 extra pins from the circuit, which is again a very infeasible situation. So we will see how to handle this. So this is a penalty of the structural test. Secondly, if you have to test this gate, this last input AND gate, the output can be observed because this is directly coming out of the circuit. But now see, again these inputs to this AND gate are not directly controllable, because they are being fed by these 5 AND gates. So this gate is feeding this gate is feeding. So you cannot directly control this. So for that you have to make a very different arrangement. So we will just see. So for these cases, for the output you can say this, for the outputs this gate and this gate outputs, so which we have brought them as separate pins. So this is one kind of a penalty. So if there is around 1000 such nets to be observed, then you require 1000 pins extra, which is infeasible. So we will slowly see how we can do away with this. But another more important problem that has arisen now is that, see this AND gate, this gate is directly, this was directly connected by this one, and similarly for this. Now what has happened is, you have to somehow what you have to do is that you have to control these gates. Now you cannot observe this, right. So this gate is not directly controllable. Let us again go back to the original figure. So you can see, so now what you do, somehow you have brought pins out and we can observe the value. But this gate is driving this AND gate. So I cannot apply any pattern over here directly. So there should be some extra arrangement so that I can somehow apply the pattern here. So how you can do this, because there is some gate, you see like this, say for example this is connected by another gate. Now you want to apply some pattern here. So how can you do that? First you have to decouple this gate, because otherwise this guy is driving this gate. So somehow you have to decouple this gate and then you can apply some pattern here. This is how it is being done. So you see what they have done, they have put a 2:1 multiplexer here, and then they have said that there is something called a test mode we applied. So when you say that the test mode is 0, then what happens? This output, so there is let us say that you apply 1 over here first, say in the test mode you apply 1. So in the test mode if you apply 1, then what happens? The output of the gate is through this 2:1 multiplexer gets directly connected to this AND gate and the circuit function normally. So, in this case also if it is 1, so this output is connected here and it feeds this AND gate and the circuit is doing a normal operation. But now when I want to do a test operation, so if you do a test operation, so what you need to do? You need to somehow ensure that this guy is decoupled, that is this gate should not be able to control this and this gate should not be able to control this, and we should be able to put some values here. So, now you make this test pattern as test mode as 0. So, if you make this test mode as 0, so this guy connection is crossed by this multiplexer, similarly this is 1, this gate crossed, and there are some extra add on pins, control pins, which gates are direct access to in this case. So, in this case now you can apply 0, 0, 0, 0, 0, 1 or whatever you do. So, now see what we have done. So, there was this is the gate and this is the line. So, this is the internal gate, say some other gate which is driving it. Now, to apply a test pattern, because now our idea is to test this gate individually rather than the whole circuit. So, what we have to do? So, some other gate is driving this gate. So, in the test mode somehow we have to make this gate unable to drive this, and there should be some extra pin outs which should now be able to drive this gate. So, that you can apply test patterns as you like, so that you can test this gate individually. So, this is possible in this case or in all cases by using what you call 2:1 multiplexer. So, basic architecture is something like this. In this case of 0 and 1, this is called the test mode. So, so when the circuit is not in a test mode or normal operation, then the normal net which is to be feeding is connected, so it feeds there. But when you make the test mode equal to 0, that when you want to do the testing, so this normal cloud or normal combinational thing which is feeding this gate gets decoupled, and there is a separate pin out that is called the test pin you can call, then this gets connected to this gate, so which is driving it, and you can apply test patterns to test the circuit directly. So, this is called controllability. So, what we have to do in case of structural testing, there are two things. One thing is observability, that output of these gates has to be observed. So, this you can very easily do by bringing these two extra pin out, that is called observable pins. This is called observable. Now, you have to also apply to test these gates, because these two pins you cannot control directly because these gates are feeding. So, what you have to do? You have to put this 2:1 multiplexer arrangements, so that these lines also become controllable. These are actually called controllable stuff. So, what happens? So, in structural testing, what we have done? We have brought down from 2 to the power n to some k. So, in this case, this was 6 into 2 to the power 5. But what we have to do? We have to have some extra pins. So, how many extra pins? For these 5 gates, we have to have 5 pins extra, and then again that is for observability, and now for controlling this inputs of this gate, you require how many control pins? There are 5 pins for this. So, you require 5 extra pins, that is the control pins here, and as well as what you have to do? As well as you have to put some multiplexers. So, how many multiplexers you require in this case? So, in this case the multiplexers will also be 5 muxes. So, this is how it is a very difficult problem, or you should not call it a difficult problem. You say that you have to apply some more penalties, like structural testing is bringing down the test count, but you require extra pin outs and you require extra multiplexers. Okay, so, extra pin outs is very difficult, because if you have 1000 lines, then you require around say 2000 extra pins or something. So, a circuit having extra 2000 pins is a very infeasible situation. So, let us see how we can handle this. So, this is what we have been discussing. The number of test pattern requires in this case were 6 into 2 to the power 5, which is around 160, which is much less than 2 to the power 25. So, if we are having the same tester, which is 1 megahertz tester, then the time required for testing is only this much seconds, and if you have to test a million samples, then you require only 16 seconds. So, structural testing is what has to be adapted, but that is very good, but the penalties of extra pins, extra muxes, somehow we have to take these things into picture. So, now we will see how we can handle this. That is, people could have not yet solved the proper, in functional testing is very good, because you need not have extra pins, you need not have extra muxes, but still you have to, number of test patterns are very high, 2 to the power 25 in this case, and the frequency, if you cannot apply the test patterns at very high speed, then test timing is infeasible. But in structural testing, you can see that in 16 seconds we can test 1 million samples, but extra pin out and extra muxes are there. So, research now have been done, so which we will study in this course, and mainly maybe so we will see something in this lecture today also, that how pins and multiplexers can be brought down that is feasible, but still taking the test frequency higher and going for functional testing is a difficult problem. So, that is what about the structural testing penalties which you have discussed. So, you require what you call extra pinouts and some multiplexers. So, I mean these requirements are actually directly infeasible. So, you cannot have that high requirement. So, let us see how we can handle the problem of extra pinouts and extra multiplexers. So, we will take a very simple another example with of structural testing with internal memory. So, our main goal is that we cannot have so much amount of pinouts. Say for example, I say that I give you 2000 flip flops, or I say I give you 2:1 multiplexer, 200, 300, 500, 1000, whatever is possible I will give you, because they will only increase my circuit area. Okay. But if I have a chip size of this much, so there is a fixed number of pins which can be applied on the circuit. If this goes to 20,000 or something, then it becomes infeasible to manufacture a device. So, 20,000 sample chip will may be as larger as this, what you call this whole what you can call even maybe as large as your what you call your laptop. So, this one chip size may be as large as your laptop if you require so called your 20,000 input pins. But this is also not a very good idea, but still I can say that I cannot manufacture a chip which size is about a laptop, but still I can have a chip and I can give you another big area in the chip itself where you can have 20,000 muxes. That is still possible, not desirable, but still possible. So, let us see with an example how we can do away with this major blackmail or major nightmare problem of the pinouts. So, first we have to handle the bigger problem, that is of the pinouts, and then we will see the problem of the lesser dimension, that is actually the multiplexers. So, this is a what you call a ripple carry adder, you can see those are the 32 bit ripple carry adder, 32 bits are the inputs and this is the carry and this is the sum, and then you can have a carry out. So, obviously, if you want to do a structural testing, you require 2 to the power 32 input patterns, that is again infeasible in terms of time. So, how to handle this? So, let us do a structural testing here. So, structural testing in the last case, the structural testing was the gate was the unit, that we were testing a gate at the unit level and we were testing the interconnects. Now, in this case we will not consider gate as a unit level, we will take it up to a bit broader level where each full adder is the unit. So, we will consider this as a unit, we will apply the patterns here and we will observe the patterns here. So, there are some more gates inside, but for this testing, this kind of structural testing, we are considering this as our unit. So, basically structural testing, as I told you, is the functional testing at the unit level. So, in the general example which we follow throughout, or in the last example, the gate was the unit, but now for us this full adder actually is our unit. So, to test it, as you know that the full adder has 3 inputs, this is the A, B, this is this carry input, then you have to sum and then you have to carry out. So, now we have to apply these 3 inputs, that is 2 to the power 3 inputs only you have to apply per full adder, and then you have to see 2 outputs, that is the sum out and the carry out. So, now if you look at the structure, in this case it is very simple to apply the inputs because they are all available at the pinouts. Okay, and we are going to test each individual stuff at a level, and also the sum output is very simple, you can easily get the sum output and also the carry output. Now, the problem is that for an individual, I told you that these are your inputs, that this intermediate carry, that also has to be observed. Okay, this is the intermediate carry, this intermediate carry is going from here to here and here to here. So, this also you have to observe. So, once this thing was that we can take a pin out, but as I already told you that bringing that pin out is infeasible in terms of the number of pins. So, somehow we have to handle this one. So, how it is handled? So, in this case people have applied a very simple logic. So, in this case we have a So, we have a simple shift register. So, what do you do? So, intermediate carry output of this gate is feeding this. For the time being, forget about the multiplexer, this is being fed to the next level of the adder, and also the same thing is writing to a shift register. Again there will be another element of the shift register which will be again fed by the output of this gate. Similarly, the output of the second last full adder will again go to feed the last full adder, as well as it will also write the 31 shift register. So, we have a 32 bit shift register here. So, now what is happening? So, whenever we get the output, the sum you can observe here. So, what we are going to apply? So, we are applying all the patterns for a full adder. Now, the sum you can directly see here, and the carry is propagated from this one to this one and so forth. At the same time, instead of drawing the pinouts of this carry, so what we are doing, we are feeding it to a intermediate which we are having a shift register. So, we are feeding this shift register. So, when all the testing is done, so all these units of this shift register have the values of this 32-bit intermediate carry. Then you can apply 32 clock pulses, so that this data is arrived. So, now in this case you require 32 clock pulses to get the result, because now we are not bringing this parallelly this output of the carry, rather what we are doing is that we are feeding this carry to these units of shift registers. So, now once the testing is done, the shift register will be loaded with this value, and in single go you cannot have the result, we have to shift out the result in a sequential manner. So, 32 clock pulses will be required, or I mean order of 32, I mean you can forget out this last carry bit. So, they have to be shifted out of this thing. So, now still you cannot say that I have totally done away with this pin business, because we require one extra thing, that is there will be a clock for this shift register and as one pin to bring it. So, what we have achieved? So, if you directly bring out this carry outs from all these adders, then you require say around 31 or the order of 32 kind of pins. Okay. And now what we have achieved? We require only one clock pin and one shift pin, that is shift out, you can call data register out, that is observation of the carry. So, instead of 31 or 32 pins, in this case we have got a what you call 2 pins we have done with this. But what is the penalty paid? Now, the penalty paid is we require 32 clock pulses to get the value. Now, there is another point, that is about the observability. Now, if you look at this full adder, so what you have to do, again this full adder, these two are the inputs A and B, which can be directly controlled, but there is another full adder here which is directly feeding to this carry. So, somehow we have to, again when you are going to test this full adder, we need to somehow decouple this, as in the last case example of the AND gate we have seen. So, you have to decouple this somehow, and then we have to apply the test pattern whatever is required. So, same philosophy we apply our 2:1 multiplexer over here, and there is the test control. So, whenever test control is say 0 or whatever, so you get in one control this output of this will feed this, the output of this feed this and so forth, and whenever you are in the test mode, then what will happen, this guy will be discoupled, this guy will be decoupled, and you can have a directly control of this, what you call this multiplexer, sorry, this array, this carry through the multiplexer. So, in this case you have see what happens. So, in the test mode this is decoupled, and this we can have direct control of this carry by this multiplexer. Now, in the last example we have seen that to control this, we have directly brought this as a pin out, we have directly brought this as a pin out, we have directly brought this as a pin out, which was again actually taking a huge amount of area, huge amount of pin outs. So, now again to solve the problem, they have again put a shift register over here. So, whatever carry values you require at this, you can shift in a shift register slowly, that will again take 32 clock pulses, because now you cannot feed everything directly, you have to do slowly in 32 clock pulses, but now this again only another pin out is required. So, instead of directly controllable pins which you have brought out, and also the observable pins which we required to be brought out in the previous example, now we are putting a shift register. So, the shift register is requiring only 2 extra pins, that is actually your clock pin and your shifting in pin, so that you can get the data ready in the individual points. It of course takes some clock period, but you are hugely reduced in the test time, you are hugely reduced in the number of pin outs. So, structural testing with internal memory reduces your pin outs, but we actually require more number of same number of multiplexers, but now we have added 2 new shift registers. But as I told you, increasing area in a circuit is still feasible, but we cannot allow to increase in this case 64 more pins, because you require some pin outs for each of the outputs of this carry, last is already there. So, you will be requiring 31 pin outs to observe the carries, and also you require 31 pins to control the individual carries. So, this is not at all possible. So, that is actually more 60 to test a circuit, you cannot double up your pin counts or have such a huge number of pins, because then the circuit itself or the package itself will be having so many pins that one chip can be as large as maybe your laptop. So, by using this internal shift registers, we have solved the problem. So, So, in this case we have solved the problem, but again we have added some more area which is for the registers. Now, we will see how can we again solve this problem, okay, of how can we minimize this area of the extra this thing. So, you see what we have discussed, that if we are doing structural testing with internal memory, we require internal registers, that is fine, but the huge number of pins have been solved. So, what is the number of shift registers? You can say that is equal to the number of internet lines that have to be tested. So, if there are 10,000 say internet lines, then you require around say 20,000, I mean 20,000, then you may require order of 20,000 blocks or 20,000 flip flops in each shift register. That is, I mean for each net you require one element of the shift register. I mean shift register consists of flip flops. So, one flip flop per net to be controlled. So, that is also a very high in number, but still that is a less amount of a problem than the pinouts. But now we will see how we can also handle the issue of this large number of pins, large number of this internal shift registers. Okay. So, now we will see, so structural testing with fault model will actually solve the problem that we will see. Okay. So, now we can say that there are some key terms like structural testing is the functional testing at the lower level than the basic input output functionality of the system. That means what? So, if you have a circuit says like this, so if you want to do a functional testing, then you have to say verify that whether my 2 to the power n systems are verified, I mean 2 to the power n number of inputs are verified. But now if you are going for structural testing, then you can break up your circuit into individual blocks, and then we find out whether you assume that you have to just test whether these blocks are individually correct or not. Inside these things we are not bothered. So, in a general structural testing, which we is the term which we use in testing, the basic block levels are the gates, and sometimes we can even go up a bit higher, like in the previous example our unit was a full adder. We were not bothered to go inside the adder and test it, but rather we were finding out that structurally the interconnection should be fine, and our case we were functionally testing the full adder, and inside we were not going, and structurally we were testing the that is whether each full adder is structurally proper or functionally proper or not, and the full 32-bit adder we were testing structurally. In other words, our full 32-bit adder was the unit or the functional circuit. So, that was the functional element, and the block levels were the full adders, and we were testing these were as the units. But in the example before that, our circuit was 25-bit input ANDing, and our individual block was a gate. So, in testing, in the taxonomy or in the terminology of testing, what you called this unit is a gate. So, we do not, I mean generally do not go to an abstract level like adder or something like that. Our unit is generally testing. So, in this case the bitwise ANDing unit, the structural unit was a gate, and the 34-bit adder, the full adders were the units. Okay. So, in digital circuit, structural testing basically functional testing at the unit of gates and flip flops. So, flip flops and gates are considered as units in the general structural testing terminology. So, only for the example we had showed you for the full adder, but you cannot go think that is a general terminology kind of a thing. This was only for the example to illustrate that what is the structural testing and what is the functional testing. So, till now we have seen that functional testing is difficult because of the exponential number of test patterns, and structural testing is beneficial because it can give you a very less number of test patterns, as well as you can have what you can call, we can have k number of pins, k number of test patterns, which is much less than 2 to the power n number of test patterns, yet the accuracy is very high, as large as 99.9% plus. But what we have problems, the problem is the huge number of pinouts, and also there can be large number of internal 2:1 multiplexers and what you call registers. So, we have seen that by using registers we can still save a lot amount of the pins, but still the number of registers was yet the problem. So, number of tests, large number of input patterns we solved using structural testing. Then using the internal registers we have solved the problem of large number of pinouts in structural testing. So, initially what you have functional test, then that is 2 to the power n. So, use structural test, then we brought it down to k, then we have large pins, large pinouts, then this we have solved using the registers. So, now we are in a position that we have a huge number of registers. So, this is what is our flow. So, now what we have to solve? We have to see how we can solve the large number of registers in and also 2:1 multiplexers in structural testing. So, again what came into the solution is structural testing with fault models. So, now again what we have seen in the last example, that we have a structural testing like a gate as a unit as a gate or a full adder, then what do you verify? We verify that whether the AND gate is functionally correct, that is 0 0 0 1 1 0 1 1, and in case of full adder we have to verify whether it is doing the addition, whether sum and carry out is proper or not. But if we go for a structural testing with fault model, we will even forget that an AND gate is an AND gate and a full adder is an adder. So, what we will verify is, given an AND gate, we will assume that it do not have any fault from the fault model. So, we will see, we will elaborate in this, but now the philosophy in structural testing with fault model is that we will not even think that an AND gate is an AND gate or what do you call the full adder is a full adder, that is we will completely forget about the functionality of the units. So, what is a model basically if you ask me? So, model is basically a representation of the circuit or representation of a system in a very simple way, but it actually have to have all the properties or as high as amount of properties which is required for the particular application in question. For example, now our problem is to test a circuit, that is we have to verify that whether the circuit is correct or whether the circuit has any defects or not. So, for that if we have some model, then our model should be enough only because see if you are testing, our goal is not to find out whether an AND gate is an AND gate or an OR gate is an OR gate. Basically, our main goal is to find out whether the circuit is having any defects or not, or the circuit is having fault or not. So, for that if we can find out any fault model which need not be functionality of the gate, but still if it can serve the purpose of testing, then we have got a very good fault model. So, for a fault model basically reduces the complexity of representation, but at the same time you have to understand that it represents or it does your job or does the job or specific or meets the specification for that particular context, in this case which is a what you call in this case is testing. So, we will take an example so you can understand better. So, this is an AND gate. So, we have already seen that AND in case of NAND gate is so complex, it has a transistor level, it can be fault, layout level it can be fault, so lot of faults can be there. So, for example, let us assume that this is a stack open fault. Okay, this line is somehow cut, this input is somehow cut. So, this is actually called the defect, that the layout is not proper, this layout should be metal should be like this, but somehow there is an opening. So, this is called the error. So, there can be hundreds of or thousands of defects, sorry this is called defect. So, there can you can say that this is the wear, so the wear is as thick, for some place maybe the wear is not cut, but this has become very thin, so that can be a defect. So, it can be saying that somewhere the line is bit thick, that can also be a defect. So, that is very difficult, you cannot do all the testing in this small amount of time it is given. So, in this case this is stack open, somehow this is the defect. Now, what is an error? So, error is actually representation of this defect. So, in this case if you apply everywhere 1 and so forth, then the answer should be 1 in the normal case, but in the error case it is 0. So, error actually represents the manifestation of this defect. Now, you can see, now I can say another way that there is a fault. So, this is the error is the manifestation of the defect and fault is the logical representation. So, you can say that this net is stuck at 0 and also this net is stuck at 0, because whatever value you apply, this can net never be 1 and this gate can never be 1. So, structural testing or fault model basically says in this one. So, I will just say in another words. So, if you want to do a structural testing of the gates, so you have to find out that you apply 0 0 0 0 0 to all ones, and then you have to find out whether the output is 0 and 1 in the respective cases. So, that is about the structural testing of the gate at the functional level, because I told you structural testing is at the gate level is functional testing of the gate, but that requires lot of registers and so forth. So, now what in fault model it says that is I say that if this line is open, that is a defect, because because I am doing testing. So, I am not interested to find out whether this gate is functionally correct or not, but rather I am motivated to know that there should not be any defect in this circuit, because that is testing. Testing in case of circuit is not to guarantee or not to ensure that the circuit is functionally proper. That is a very difficult, because it takes long time. So, what I want to do is that I want to find out that there is no defects. But testing for no defect is long time, because you have to, there is lot of physical defects, there is lot of crystal defects, and it goes into physics. So, what I can say that if I say that this line is stuck at 0 and this line is stuck at 0 in this case, because in this case we stuck at 0, if I apply anything this line can never be 1, and similar in this case. So, I can say that this line is stuck at 0. So, if I can ensure that this line is not stuck at 0, stuck at 1, this line is not stuck at 0 and stuck at 1, similarly for this case and similarly for this case, then I can say that my AND gate is not having any kind of stuck at 0 or stuck at 1 faults. So, we are not saying that the gate is an AND gate and is properly behaving or the functionality is correct, but we can only say that the structural testing says that this AND gate does not have any stuck at 0 at this point and neither in these lines. So, this is actually called structural testing at the fault model. Now, what is the fault model in this case? The fault model in this case is the stuck at 0 and stuck at 1, because it is a digital circuit. So, each line can be either normal, stuck at 0 or stuck at 1. So, this is how it can be done. So, now we will see how we can, or I mean maybe in this lecture or in a few more lectures, we will see how this structural fault model helps us to reduce the problem of resistors. So, there are different fault models. So, stuck at fault model is what? Each line can be stuck at 0 and stuck at 1. So, there can be a delay fault. So, in delay fault, these lines do not have a stuck at 0 or stuck at 1, but in the normal time, if you require n amount of time to rise from 0 to 1, in a delay fault, the delay will be higher. Similarly, in case of this is rise delay, similarly there can be a fault delay, so the delay will be higher. So, this is about a delay fault model. So, that is circuit is normal or the logic is normal, but there is a delay to rise and fall. Then there can be a bridging fault, that is in between two lines there can be a short. So, these are some complex fault models which we will not study in this course. Mainly we will see this stuck at fault, which is the most widely accepted fault model, because it has been seen that if you can adhere to this fault model, a large number of faults of this nature and more advanced nature gets captured. So, we will see this fault model. So, let us see how a fault circuit with a fault model will look like. So, this is a circuit. Now, in structural testing what we have done, we have to test this guy individually, we have to test this guy individually and this guy individually. For that we have to observe this at the output, so you have to bring them to the output. Then we have to control these two guys to test these two things. Then you have to put a 2:1 multiplexer here, and then you have to either bring this controlling line out, or you have to have a 2-bit what you call register here to control these things. So, that was the main difficulty in this case. Pin outs we have reduced by the what you called the registers, but we could not have done about with the registers, that problem was still remaining. So, now in this case what we have done, so if you are doing a structural testing not at the functional level, that is the fault level, fault model level, then what we have to verify? We do not have to think that this is an AND gate, we do not have to think this is an AND gate and so forth. We have to just verify that this line does not have a stuck at 0 and stuck at 1, this line does not have same stuck 0, stuck 1 and so forth. So, we are all the full circuit, we are breaking down into individual nets. This is one net, this is one net, these are the two nets, these are the two nets, and this we will see, these are fan out, this has to be handled separately, we will see. So, each of the nets you individually consider and apply, you have to apply a test pattern which will verify that none of the gates have a stuck at 0 or stuck at 1 fault. So, now we are doing a structural testing, but this is not at a functional level. And it has been shown that you can, if you can do this, then also the test coverage is as high as again 99% accuracy. So, slowly we have to see how, that means in a few lectures down the line we will see how this structural testing with this fault model will help to reduce the number of registers, number of pin, and everything will be very neat. But for the time being, just take it for granted, take it from my side, that if you can if you even test a circuit forgetting about the functionality of the AND gates and just verify that these nets do not have a stuck at 0 and stuck at 1 faults, still the coverage is as high as, or you can say that the accuracy as 99.9% plus. But there is a very interesting fact here which I should mention, that this is an individual net, fine, these are two individual nets, fine, but this is a single electrical net. Okay, but still for the stuck at fault model says that you have to consider this as an individual net, this as an individual net and this as an individual net. That is a fan out, if this is a fan out, you can have a stuck at fault here, then the stuck at fault may not be here, you can have a stuck at fault in this, then these two lines are free of stuck at faults, then it may happen that this guy is not having any stuck at fault, the third net can have a stuck at fault. Even this whole line is electrically single, but this are having 3 faults, I mean 3 individual faults can be there. Now, you can ask me the question, why is it so? The answer is, this has been found statistically, that is because the circuit generally do not have a stuck at fault. Now, only what we are verifying, that we are saying that if you apply test patterns which verify that these lines or this circuit is free of stuck at faults, then you can say that what you can say that so what I was saying, that we are not in fact testing, we are not testing what? So, we are not trying to ensure that our circuit is free of faults, which we are trying to ensure, say that we are not trying to say that the circuit is normal. Rather, what we are saying, we are trying to say that our circuit is having no stuck at faults, that is what we are trying to say. Then you are saying that no stuck at faults, stuck at 0 and stuck at faults are not there. Okay, then it implies that circuit is 99.9% plus chance that normal. But we are not actually telling the other way around, that we are not claiming. We are not saying the other way that if the circuit is normal then no stacked fault kind of, this is not our claim kind of thing. So what we are trying to say that we are verifying that the circuit is having no stacked faults, then it is 99.9% chances that the circuit is a normal behavior. So they say that if we treat this as a single net, then it has been found out, I mean by statistics of the history, that if we only consider this fault then the accuracy is lower. So we have to also consider this as an individual net and this as an individual net. So basically this is a model. In reality circuit does not have stacked faults kind of a thing. It is not as good or as neat as a single stacked 0 and stacked 1 fault. Only we are verifying that no stacked fault, implying that the circuit is normal. So for that reason we have to also consider these things. So generally you can ask me that how many stacked faults at a time. So basically the idea is that you can say that you can have one line, each line can have a stacked fault. Now pair of lines can have a stacked fault, 3 lines can have a stacked fault, and dot 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 dot. But if you consider this, the number of stacked faults will be extremely high. It will be actually 3 to the power n minus 1, because normal, stacked 0, stacked 1. So if you consider all combinations, it will be 2 to the power 3 to the power n minus 1, which is a huge number of faults. So you cannot do away with it. So it is very difficult to handle it. So again statistically it has been found that if you consider single stacked fault, that for actually what is a single stacked fault? You have to think that only one fault at a time. I will consider all the stacked faults, that is true, but first I will find out that this fault is not there. Then I will assume that if I find that this fault is not there, very good, then I will test for this one. This fault is not there, then it is fine, and so forth. So I will consider one fault at a time. So if there are n nets and I consider one fault at a time, so how many faults are there? It is actually 2n. So if I consider all combinations, that is this line, this line, this line, this line, and so forth, all combinations if I take, then it is 3 to the power n minus 1. Okay, but if I consider that only one fault can happen at a time, but I will consider each one, but individually one at a time, then it is only 2n. And statistically it has been found that even if you are taking single stacked fault model, that is handling multiple faults is very infeasible with huge number of nets, but single stacked fault is manageable in the number, and it also provides acceptable test quality. That is, we are taking one net having a stacked 0 at a time, verifying it is not there, then we are considering the same net with stacked 1, verifying it is not there, and stepwise one at a time for each net if we verify, then it is called single stacked fault. The number of faults are 2n if the number of nets are n, then the number of faults are very manageable, because 10,000 lines in a circuit means only 20,000 number of faults, and then you can say that, and also it has been found out statistically that this is a very acceptable fault model, because of what you call this a very acceptable, because this type of testing people has found that the accuracy is around 99.9% plus. Okay, so that is why the single stacked fault model gives only 2n faults, wherein the number of nets in the circuit, as well as the accuracy is also 99.9% plus. So people have found out that single stacked fault model is a very good and a widely adapted fault model. So in all future discussion we will be using a single stacked fault model. So some examples, if I can ask you, how do you test using a single stacked fault model? So let us consider this circuit. So let us say that this net is now having a stacked 0 fault. So to test a stacked 0 fault, what you have to do? You have to apply a 1 over here, because this is stacked 0, you can assume that the electric bulb is fused. So to test that the electric bulb is not fused, what you have to do? You have to put the switch on. So in this case it is stacked 0, so you have to apply a 1 over here. So you have to apply a 1 over here. Now you can understand that to see that whether means that is what will happen if the circuit is having a fault, you will get the answer 0 because of the stuck nature, and if the circuit is normal you will get a 1. But now it is an AND gate. So if I put a 0 in the last net, say in this net I put a 0, then what will happen? Irrespective of fault is there or not, the output will be 0, because this guy will be controlling this output. So to avoid this, what we have to do is that we have to apply all the other lines as 1 1 1 1 1. Then what will happen? I will apply also a 1 at this line. So what is happening if I apply 1 at all the lines, then what happens? In the normal case the answer will be 1, but if there is a stacked 0 in this net, the answer will be a 0. This is for the fault and this is for the normal. But if I somehow apply a 0 over any other cases, then this effect is not brought out in the picture. Similarly, so this is what you are getting, 0 if the fault is there and 1 if the fault is not there. So again this effect I have to propagate to the output. So what I am doing, I am not, as I already told you, neither I am putting any pinouts to observe this output, neither I am going to put any multiplexer or any register for that. So now the fault effect is here, that is 0 if the fault is there and 1 if the fault is not, but I am not able to observe it, because I have not got any pin out here. So, no pin out is here. So, I have to propagate this value through this gate. Okay. So, now what I do, if somehow I get a 0 over here, then the fault effect propagation is not there because 0 will be propagated. So, what I have to do, so to keep this effect here, I have to apply 1 over here, I have to apply a 1 over here and so forth. So, to get a 1 over here, all the inputs of the all other AND gates should be 1. So, the input pattern 1 1 1 1 1 1 all ones. If you get the answer 1, then you can say that the stuck at 0 fault is not there, and if you get answer is 0, then you can say that a stuck at 0 fault is here. So, by applying this pattern, you can ensure that if the answer is 0, the stuck at fault is there, and if the answer is 1, then no structural fault is there. So, structural testing with fault model stuck at 0 1 fault, by applying this pattern, what we have verified that without using any extra pin or without using any extra stuff, we have verified that a stuck at fault 0 fault is not there. Now, if you simply reverse it, if you say that there is a stuck at 1 fault over here, now same thing, it is stuck at 1, so I have to somehow apply a 0 over here. So, I put a 0 in this case, and because of the observability thing, that is, I told you that the fault effect, this effect that if the circuit is stuck at 1 here, I put all 1 1 1 1 in this input of the AND gate. So, if the circuit is normal, so this is 0 you have applied, the answer should be 0, and if this net is somehow stuck at 1, so you will get a 1. So, this fault if have to be, the effect has to be propagated through this AND gate, all the other inputs have to be 1 1 1 1. So, the pattern, this one, that this net is 0 and all other are 1s, will actually propagate this fault effect to the output. So, what is the effect? The effect is 1, if there is a stuck at 1 fault here, the answer is 0, this circuit has no fault. So, this is the pattern which verifies that there is no stuck at 1 fault at this net. Similarly, we do not require any extra net or any extra controllability to test this one. So, we have seen that structural testing with stuck at fault model is really very helpful in the sense that we do not require any extra pin outs, as well as we do not require any multiplexers or what you call the register. But somehow we have to find out which pattern to apply to test this as stuck at 1 fault. So, for this net we have tested for stuck at 1 and stuck at 0. So, we have found that if all ones you apply, you can test for stuck at 0, and if you apply this pattern, then you can apply test for a stuck at 1 fault. Similarly, we have to find out patterns and repeat it for all the nets here, all the nets here and all the nets here. So, this is actually called test pattern generation, which we will slowly see. Okay. So, what are the pros and cons with structural fault models? The pros are, we do not require any extra test pin or any extra multiplexer or any extra stuff like registers, etc., multiplexers, pin outs, etc., to do the testing. So, we are able to find out that there is no stuck at fault just by giving some inputs, and test time is very low, because we will see how these things we will see later. The test time will be lower because in one test pattern you can test multiple stuck at fault. That things will slowly come into picture. And what is the cons? What is the disadvantage? The disadvantage is that functionality is no longer tested, and yet you are not testing, you are just verifying whether there is no stuck at faults are there or not. But still history has showed that even if this functionality is not tested, even at the unit level, still the test quality is guaranteed to a very, very high level. So, that is why what you call structural testing with fault models is widely accepted. So, before we finish our lecture today, so we will go for the question and answers. So, we will be putting the questions today, and in the next lecture maybe, or just before we go to the motivation for what we have finished today, we will go for the answers of the question. So, what is the questions? The first question you should be answered is that what are the problems of structural testing without fault models? Okay, so we have seen that the structural testing can be done with fault models and without fault models. With fault models, what are the advantages? No requirement of extra pins, no requirement of multiplexers, no requirement of what you call the flops and registers and all those things are not required. Okay, but but if you have that is with fault models. Okay. And so, the question we are asking is, what is the problem of structural testing without fault models, which I have said, if the units are gates as well as the units are larger. So, one thing you can say about this, we require a large number of flip flops, we require a large number of registers, we require a large number of extra pin outs. But you have to answer what is the impact. That without fault models means you require a lot of extra arrangement like pin outs, as I told you, gates, pin outs, then you require 2:1 multiplexers, then you require what you call registers and so forth, if you are doing without fault models. Now, if the units are gates, what is the impact, and if the units are very, very large, then what is is the problem? So, we have to think of the answer in this way. We all know that this extra stuff will be required if you are doing without fault models, but what is the impact if we consider gate as the block and if you consider adder or full adders, half adders as the blocks, then what is the impact? So, that we have to see. The second question is that we have found that structural testing with fault model is very good. Okay, then, but is it really happens that the nets really gets stuck at 0 and stuck at 1 as neat as that or as simple as that? If it is not so, then why is single stuck at model so relevant that we can do the whole amount of testing and we can assure that functionality is tested, structurality is tested, and I mean we should not say that functionality is tested, we say that we can say that 99.9% you can be sure that if there is no stuck at fault in this circuit, then it is 99.9% tested accurate to be functionally correct and so forth. That is a huge accuracy you are getting. So, how is it possible and why is it so? Because this the question is, these nets in the circuit do not really have such a neat stuck at 0 and stuck at 1 fault, because in the real world there are defects like the net may be torn, the net may have become thinner and so forth. But still, why is then stuck at fault model? If really it is not happening at the level, then why is stuck at fault model so relevant? So, these are the two questions we are putting into picture. So, we can go through the lectures and then think over, and in the next lecture before we starting it we will go for the answers. Thank you.